dear students, in physics now we are going to see another experiment. What we are going to do here is to determine the mass of a body using the principle of moments. You know the principle of moments, right? When a body is in equilibrium, there are a couple of conditions that it has to satisfy to be in equilibrium. First one, whichever the direction you resolve the forces have to be summing up to 0. Total of resolved components must be 0 in any direction, thereby resultant is 0, and moment of forces from any point will be 0. Moment of forces from any point will be 0. So, look at this now. What we are going to do in this experiment, let me explain to you. We will take a meter ruler. We will take a meter ruler. Right, this is the meter ruler. And we are going to balance this on a knife edge. Knife edge. I will explain what is knife edge. Right. Actually, something like a prism. It's a wooden prism, right? Prism shaped wooden block, which has a very sharp edge. Because what we want here is the meter ruler to touch its base, to touch this wooden block at just one point. We don't want a situation like this. Meter ruler is this, and we don't want it to touch at a plane. Then it's very difficult to decide at which point the reaction comes. So, to avoid this, what we want is the meter ruler to be balanced at one particular point only. That's why we call it a knife edge. So, it's not a knife that we are using, right? But why we call it a knife edge is the edge of that wooden block is as sharp as a knife edge. So, the contact will be only at just one point contact, right? Then, so what do? We just adjust the meter ruler here and there, and we balance it. It has to remain horizontal on this knife edge. When it remains horizontal on this knife edge, what are the two forces that act on this meter ruler? First one has to be the weight of the meter ruler. The weight, it will have a weight that will be vertically downwards. Second one, the normal reaction from the point of contact. So, this knife edge will give a reaction. That reaction will be, like what we studied about reactions. If on a plane, if you keep something, then the reaction will be perpendicular to the plane, right? If you keep something on an edge like this, if a point contact is there, normal reaction will be perpendicular to this rod or whatever. So, here the normal reaction will be perpendicular. Well, so those are the two forces that are going to act on this meter ruler, and the meter ruler is going to be in equilibrium, right? If two forces act on a body and if that body is in equilibrium, what can you say about that? Both forces should act on the same line of action. Both forces must be equal in magnitude. Both forces must be in opposite direction, opposite sense. Then only it will come to equilibrium. If it is not on the same line of action, if there is a gap between the line of actions, then even if the forces are equal, it won't be in equilibrium. It will start rotating. There will be a couple of forces. Basically, there will be moment, right? So, if two forces act on this meter ruler and if the meter ruler is in equilibrium, the two forces must be on the same line of action, must be opposite in direction, must be equal in magnitude, right? We know normal reaction has to happen at this point itself. Normal reaction must be like this. If normal reaction is like this, then obviously the weight also has to act on the same point. Weight of the meter ruler. That's how it can be in equilibrium. If weight is not at the same point, it won't be at equilibrium because there are no other forces. It's in equilibrium only with two forces, right? Then this point can be called the center of gravity of this meter ruler. We usually mark it as point G. Center of gravity of meter ruler. Why? The point where the weight acts, is what you call the center of gravity. So here we have found out this is the point where the weight has to act. So that's what our center of gravity is. So this is what the first step we are going to do, balancing the meter ruler on a knife edge. And this knife edge, this is a small prism like couple of centimeters height. So to elevate this system, what we do, we keep a wooden block under this. Right, you keep the whole thing on a wooden block and elevate it. I'll tell you why we elevate the system. Now what we are going to do on this meter ruler is to hang two weights. So you need the height to hang it. If it is too close to the table, then you can't hang it, right? Imagine if the table is here, you can't hang it. Now the table is going to be down here. The table will be here. This is what the table is. Right. So this is the table. This is a wooden block. This is a knife edge. Right, this is a meter ruler. Right, system is ready. Now what do? We are going to hang two weights on either side of this meter ruler. See what happens. What is this? One is a known weight. This is a known weight. Might be 50 gram, 100 gram, the weights that you have. So this is a known weight that you attach here. On the other side, you attach an unknown weight. The weight of that only we are going to find. See, determination of the mass of a body using the concept of moments. So this is the body with unknown mass, right? Now let's mark the forces. Look at this. Here you will have, let's say, M naught G. Here you will have mg. M naught is known, M is not known. Right? So what we will do now, usually we keep this in a known distance. Let's say you keep it at 40 centimeter, 20 centimeter. Likewise, you keep this in a distance that you already planned from this point. Where do you think this point would be? This is a 100 centimeter meter ruler. If the meter ruler is uniform, it will be at 50th centimeter. But usually you won't find perfectly uniform meter rulers because it's a wooden meter ruler, right? So it may not be perfectly uniform. Then, around 50 centimeter, somewhere around 49, 51, in that range you will have the center of gravity. Don't expect this to be always at 50 because you don't find uniform meter rulers in the laboratories. It doesn't work. Now, so from here, suppose if it is at 49, keep this at, let's say, 9 centimeter from this side. That means this point to the thread here is 40 centimeters. Keep it like that. And then you have to adjust this, right, in and out until this system comes to a balance again. So make sure knife edge is at G itself. Already, like before you hang these two, you would have found out where the G is, right? Let's say the G is at 49 centimeter. So every time you have to ensure the knife edge is at 49 centimeter. Because if it moves here and there, then all gets wrong. So make sure that point doesn't change. And you keep the known weight at a known distance. Let me call it X. Let's call it X. Let's call this X. And then adjust this until this system comes to an equilibrium again. When it comes to an equilibrium, let's say this is Y. Let's say that's Y. Now what do we do? About point G, take moment. About G, take moment to this system. Since you take moment about G, R and W wouldn't come because they go through the point G. There won't be perpendicular distance. Moment is force into perpendicular distance, right? Force into perpendicular distance. So there is no distance for R and W when you take the moment from G. Then you are taking clockwise that mg into y. This is going to be counterclockwise minus m naught g into x. That's all the moments you have. And this has to be 0 because what? The system is in equilibrium. System is in equilibrium. When it is equilibrium, remember I told you whichever the point you take the moment from, the sum of the moment has to be 0. Moment must be 0. Made it 0. Now G and G will cancel. You can say M equals M naught X over Y. So if you know X, if you know Y, you can find M, because M naught is a known value, X is a known value, Y also you can read from the meter ruler, put those values, you can find M. Right? Understand one thing, if M and M naught are comparable values, if they are like close in mass, let's say one is 40 gram, other one is 45 grams, 50 grams, 45 grams. Likewise, if the two values are close, then look at this, M over M naught is going to be X over Y, right? Then X and Y also will be closer values to each other, which means if X is 40 centimeter, Y is also around 40 centimeter you will get. If X is 30, Y is also 30, which is good. So when you take this known mass, you just weigh this unknown mass with your hand and see, okay, approximately how much it would be. Around that, you have to take the other weight. The reason is, imagine if you have taken, okay, let's say M is 50 gram, which you didn't find it yet. Let's say it's around 50 gram. Having that at 50, you have got M naught as 500 grams. A very big value, 500 grams. And then you keep X at 40 centimeter. When you substitute here, M naught 500, X is 40. We need to find Y, is it? Y equals, okay. M naught over M, 40. You need 400 centimeter. You can't get that in the meter ruler. 400 centimeter wouldn't come, so you can't get the equilibrium keeping it at 40 centimeter. Maximum, if you keep the 50 gram at 50 centimeter, the other side equilibrium will happen at 5 centimeter. 5 centimeter, because 1:10 ratio is going to be 40, 400. So if this is at 50, other side will be 5. 5 centimeter is okay. The problem is the fractional error will be high when you read that. Because meter ruler, 1 millimeter error could be there. 1 millimeter divided by 5 centimeter, 1 over 50, 2% error, which is significant. So how do we usually reduce the fractional error? We measure bigger length so that fractional error, because error divided by the measurement is what you call fractional error. Make the measurement big so that your fractional error will minimize. Understand? Therefore, it's ideal to have these two masses somewhat closer to each other, not like this, right? Not like this. We shouldn't do like this. Clear? We shouldn't do like this. And in physics, most of the experiments we go with the graphical method. We don't want to conclude the value of M like this. We will go for graphical method. Why? How? Take Y here, m naught over m into x. This is in the y-axis, this is in the x-axis, this is going to be the gradient. So, you take multiple values like change the x to different values 50 centimeter, 40 centimeter, 30 centimeter. Likewise, take multiple values for x and each time balance this and find the value of y. Draw the graph x versus y, measure the gradient is equal to m naught over m. M naught is a known mass, m is the unknown mass, you can find it with the help of gradient, right. This is what the very simple experiment of finding the mass using the principle of moments. Clear? Right. Now, let us see how we are going to do it. Materials and apparatus, you need a meter ruler, a knife edge, a 50-gram weight, a glass topper or a small stone. That is the unknown mass, that is the unknown mass. A piece of string and a block of wood, right. Piece of string is to hang this, block of wood is this. Theory, that is what I explained to you now, that is what I explained, right. So, here they have taken y as the other side, y is on the unknown known mass, x is on the unknown, see m naught and y, so it comes m over m naught. However, gradient of the graph y against x is m over m naught, right. Method, place the knife edge on the stand and on it balance the meter ruler horizontally. As shown in figure, suspend the known mass m naught and the unknown mass m on the opposite sides of the knife edge and adjust length y keeping length x at a selected value until the ruler is balanced horizontally. Measure the values of x and y. Repeat the experiment for 5 other selected values of x so as to obtain a wide spread of readings. Enter the readings in the table when taking the readings. Take care to keep the balancing point of the ruler on the knife edge unchanged at the original position. Remember, I told you when you balanced only the ruler, if it balanced at 49 centimeter, every time you get the readings, ensure knife edge is at 49 centimeter. If that changes, it is all going to be wrong. It is all going to be wrong. I will tell you why it becomes wrong after that. Suppose if that changes, look at this. The meter ruler is this. Say this is where the weight is G. This is where the knife edge should be. Let us say a mistake happened and the knife edge has got shifted. It has come here, let us say. Now, you are going to have the masses here m naught, m, x, y. So, when you take moment from this point, we have to take the moment from this point always, reaction is here, right. Now, this is not G, let me call this point as A. About A, when you take moment, m into y, mg into y, mg into y, m naught g into x, and can you see this weight is also going to be there, the weight. Why? This time weight has a distance. Let this be x. It is going to be plus weight into x is going to be 0. Weight into x is going to be 0. Right? Nothing wrong in keeping like this. Suppose if you keep like this, in every reading the x has to remain same. Suppose if you are done like this, then what will happen? Now look at this. We can say y equals m naught over mx. It goes to the other side minus wx. Correct? Then you will get a graph with wx over mg. You will get a graph with intercept. And from the intercept we can find the weight of the meter ruler. That's okay. That's okay. Only thing, suppose if you keep it like this, say you are getting 5 readings. In all 5 readings, this x has to be constant. Then only you will have a constant intercept. Suppose if this is at 49 centimeter, let us say you kept it at 45 centimeter, then this gap is going to be 4 centimeter, right? Make sure all 5 readings you get keeping the knife edge at 45 centimeter, so that x does not change. Can do like that also. That is another version of this experiment where basically extension of this experiment where using the principle of moments to find the weight of meter ruler as well. Weight of meter ruler as well. Clear? Right. So, that we can do, but the original method is not capturing that. So, make sure you keep the knife edge at the center of gravity itself, and every time you have to ensure that does not change. Clear? That's what the experiment it is going to be. Shall we do this experiment and see whether we can get the readings as we want? The apparatus that are required for this, first one is the meter ruler, the usual meter ruler, which is 1 meter length, which is 100 centimeter. Each centimeter is divided into millimeters, right? So that meter ruler. And then we use this wedge shaped wooden block. Actually, we call it knife edge. We call it knife edge. When I do the experiment, I will explain you what's the meaning of this knife edge and why do we have to use this knife edge. And this is the wooden block. To raise the system up, on top of this wooden block only we will be setting up this system. That also I will explain to you why do we do that. Now if I explain, you can't understand that. When I do the experiment, I will tell you what's the purpose of this. And we have two different weights. This is the known weight. The mass of it is 50 grams. 50 gram known weight. And this is the unknown weight. The mass of this stone is unknown. I have connected both of them to a string because I am going to hang them on a string using these meter ruler, right? So that's all the apparatus: meter ruler, knife edge, a wooden block, known weight, unknown weight. Let's see how we are going to make the arrangement and do this experiment. You can see I have kept the wooden block vertically. On top of that, I'll arrange this knife edge. First thing we are going to do, we are going to take this meter ruler and balance it on the knife edge. Right? After balancing, I'll explain to you what we are going to do. Right. Now the meter ruler is balanced. Couple of things you have to understand here. First, think about the forces that act on this meter ruler. One is its weight, right? The gravitational force on the meter ruler, which we call the weight of it, which will be vertically downwards. Then the other one is the reaction from this knife edge. Since it is just a point, the reaction will be perpendicular to the meter ruler surface. Those are the only two forces that act on it right now for this meter ruler to be in equilibrium. So if it is in equilibrium under two forces, then what we can say about those two forces? Those two forces must be equal, opposite in direction, they must act on the same point. That's what we see here. The reaction acts on this point, at the same time the weight also has to go through the same point. By doing this, we can find out the center of gravity of this meter ruler. We can find out where exactly the center of gravity is. Right? And the other point you need to understand, it is 100 centimeter length meter ruler. So you may expect right at 50 centimeter we will have the center of gravity. Not really, because this is a wooden ruler. The thickness is more or less same, but remember, it's not that uniform. The thickness might differ. Even if the thickness is same, the density might differ, because this is just a wooden ruler. Wood, whether the density will be equal all over, you don't know. Therefore, don't ever assume for a meter ruler, center of gravity will be right at 50 centimeter. Can be a wrong assumption. You need to balance it like this and find out where the meter ruler's center of gravity is. Right? I have found it now. Then what I am going to do, I will take the known weight and hang it from this ruler using the string on one side of this knife edge. On the other side of the knife edge, I have the unknown weight. We will hang the unknown weight. For the known weight, 50 gram, let's keep it at a known distance, let's say 10 centimeter from the center of gravity. This is at 49.8. At 39.8, let me hang the known weight. And then unknown weight, unknown weight, I will move it and I will find the point where the system comes to equilibrium, right. So, let us say, okay, at 49.8 at 10 centimeter, or let us say L1 distance 50 gram got balanced, or it is hung there. On the other side, L2 distance, this unknown weight is hung, and the system is in equilibrium, it balanced. Now, if I take moment about this point, which point? Where the knife edge touches the meter ruler. From that point, if I take the moment, sum of moment has to be 0 from any point because system is in equilibrium. Why I prefer taking moment from that point is the reaction and the weight go through that point. Therefore, the moment of those two we don't have to consider. I have to consider the moment created by the two objects that I have added additionally, the known weight and the unknown weight. The unknown weight will give a clockwise. If I take the moment from this point, it gives a clockwise moment. The known weight attached on this side will give a counterclockwise moment. So, clockwise moment and counterclockwise moment have to be equal for the system to be in equilibrium. So, counterclockwise moment is what? M1, which is the known value, M1 50 grams, into gravitational force, let us say gravitational acceleration, let us say G. So, M1 G into L1. On this side, it is going to be M2 G into L2. When it balances, you know L1, you know L2. G and G will cancel both sides. You know M1, you can find M2. So, even with one reading, actually you can find it. M2 will be equal to M1 into L1 over L2. But we don't find it with one reading itself, because you know in physics we usually prefer graphical methods because that will improve the precision, that will improve the accuracy. So, we will repeat this process by changing L1. You did L1 10 centimeter and find L2. Then you change that to say 20 centimeter and find L2. Make it 30 centimeter and find L2. Likewise, we will take like 4 or 5 different pairs of readings. M1, L1 equals M2, L2. If you take M2, L2 the subject, L2 equals M1 over M2 into L1. Take L2 in the y-axis. L2 is the distance on this side. Distance from the knife edge to the unknown weight. L1 on the x-axis. L1 is the distance on this side. L2 on the y-axis, L1 on the x-axis. You draw the graph, you will get a straight line going through origin. And the gradient of that straight line has to be M1 over M2. M1 is the known weight, M2 is the unknown weight. You find the gradient from the graph, equate that to M1 over M2, you can find M2. Understood? This is the process we are going to take, right? So, first of all, let me see at which point this is balancing. You can see from this side, if I take the measurement, that is at 49.8 centimeter. Yes, 49.8 centimeter. If I take the measurement from this side, that is 50.2 centimeter. 49.8 or 50.2. Let us take all the measurements from this side, then it is going to be 49.8. Why do we prefer a knife edge here? Because we need one sharp point to say, okay, at this point only the weight of the meter ruler is acting. If you keep it on a plane, not just a point, if you keep it on a horizontal plane or something, then you will not be able to figure out the point at which the reaction is exerted. Then you will not be able to find out the point where the weight of this meter ruler is acting, which means you can't figure out the center of gravity. That's why we prefer a knife edge. We call this knife edge, even though I'm using a prism shaped wooden block. The technical name of this is knife edge. Knife edge. So, in the exam you can't write it as a wooden block, you can't write it as a prism shaped wooden block, you won't get marks. You have to say knife edge is used to balance the meter ruler, right? Okay. So, this is at 49.8. As I said, let us first take 10 centimeter for the known weight and see unknown weight, how much distance it takes to balance the system. Let me attach the known weight first. bring it to 39.8 from this side. And let's attach the unknown weight on the other side, unknown mass on the other side. Make sure you have kept it at 49.8 itself. Right. Now we have to balance it. Only thing I can change is the distance of this part. Let me take it here. This side it's more. On the other side it's more. So it has to be in between. This is at 49.8. Yes. Right, children, you can see this is the point, this is the position where it balances. The knife edge is kept at 49.8. The known weight of 50 gram, known mass of 50 gram is attached at 39.8. So this gap is 10 centimeter. And the unknown mass is now attached at 62 centimeter. So this was at 49.8, this is at 62, means 12.2 centimeter from the knife edge. From the knife edge, 50 gram is attached in 10 centimeter, this is attached in 12.2 centimeter. 62, 49.8, subtracted 12.2. So L1 is 10 centimeter, L2 is 12.2 centimeter. Actually, as I mentioned earlier, with this itself we should be able to calculate the mass of this. But since we are going for a graphical method, we need more readings. Now I have done for 10 centimeter of the known weight. Let's increase this to 20 centimeter and see at what distance it balances. 20 centimeter means this is at 49.8. 20 means it has to be attached at 29.8 centimeters. 29.8 centimeters. Let's see 29.8. Still not enough. Not enough. Now it's more on the right side. Make sure the center is at 49.8. There you go. At that point, it balances. Here it is at 49.8. The known weight of 50 gram is attached at 29.8. So this gap is 20 centimeter. Let's see the reading here. You get 74.2 centimeters. 74.2 centimeters. So this is at 49.8. 74.2 means altogether you have 24.4 centimeters. It is in line with the previous answer. 10 centimeter, we had a distance of 12.2. Now for 20 centimeter, you get double of that, 24.4 centimeter. Right? So that's a second pair of reading we get. L1, 20 centimeter. L2, we get 24.4. Remember, when we are drawing the graph, you can't expect all the points to exactly lie on a straight line. When we do experiments, due to practical reasons, due to human errors, there will be some errors in the experiments. So how actually we get the points little bit deviated from the straight line. 1 or 2 points might be little bit deviated. That you have to expect on any practical experiment we do. Right. So don't be disappointed or don't be upset if you don't get all the points on the same straight line. It can happen. If you have got all the points on the straight line, maybe you didn't have any errors, which is one of the rare situations, right? Or else you have not done the experiment properly, you have calculated the points and you have inserted into the graph. Even that happens when students do the experiment, and when they come up with the graph and show the graph, if all the points are exactly on the line, one doubt the teachers might get is whether the student has done the experiment or whether he has calculated the points. Understand? So when we do practical experiments, especially when we are drawing the graph, don't expect all the points to be in line with the graph. Slight deviation, if you have massive deviation, then it's a problem. Slight deviation is acceptable. Now I have got the second point. I need to get 5 points. If I increase 10 by 10, it may not be enough because 20, 30, 40, 50. When I go to 40, 50, this might even go outside the meter ruler. So now what we will do, we will increase 5 centimeter by 5 centimeter. Let's bring it down another 5 centimeter. Now it is at 29.8. We will bring it to 24.8. 24.8. Make sure the center is at 49.8. Don't miss on that. Right. Now let's move here. Still the left side is more. Counterclockwise momentum is more. Now the clockwise is more. But this is not at 49.8. Make sure this is at 49.8. That's the point where we get the equilibrium. This is at 49.8, 49.8. This is at 24.8, 24.8. So you have 25 centimeter gap here, 25 centimeter. And on this side, let's check the reading here. On this side, we have 80.6, 80.6 centimeter. So 49.8, 80.6 means if it is 50, 30.6, another 0.2, so 30.8 centimeters on this side. When you have taken 25 centimeter for the known weight, what we get is 30.8 centimeter on the other side, right? So this is the third reading, 10 centimeter, 20 centimeter, 25. Now let's take 30 centimeter. 30 centimeter means we have to move it by another 5 centimeter. Let's move it by another 5 centimeter. Let's bring it to 19.8. Make sure this is at 49.8. And then we have to increase it further. Though still anti-clock, counterclockwise it's more. Little bit. Now this is the position it balances. We have 19.8, 49.8, 30 centimeters here, 30 centimeters, 49.8. This is at 86.7, 86.7 means altogether it's 36.9 centimeters. 30 on this side, 36.9 on the other side where we have attached the unknown mass. That's reading number 4. 30 centimeter on the known masses side, 36.9 centimeter on the unknown masses side. We have taken 10, 20, 25, 30. Let's take one more reading. 5 readings will be more than enough to draw a straight line. So this time let me move it by another 5 centimeter, take it to 14.8 centimeters, 14.8 centimeters. Right, this is at 14.8, this is at 49.8, don't change that. Still not enough. That's at 49.8. This is at 14.8. And here we get 92.7 centimeter, 92.7 centimeter. 14.8, 49.8 means 35 centimeters on this side, 35 centimeters on this side. 49.8 to 92.7 means 42.9 centimeter on this side. 42.9, 35, 42.9. So we have got 5 pairs of reading. As I mentioned earlier, this is the known reading, known length, let it be L1. This is the unknown length, let it be L2. L2 versus L1 graph, if you draw, then you will have M1 over M2 as its gradient. So from the graph, you find the gradient. M1 is this 50 gram, M2 we don't know, we can find M2. Right? So let's draw the graph and see how we are going to get it. There is a couple of other things that we can do with this same experimental arrangement. Now we know the point where the center of gravity of this meter ruler is, but we don't know the mass of it. Using this setup, we can find its mass as well. How? The experiment we did now, we kept the knife edge at the center of gravity itself. The option we have now, don't keep it at center of gravity. After finding the center of gravity, you know center of gravity is at 49.8. Now let's move it and keep it at another point. Let me keep it at 44.8 and balance the system. Right, now what will happen? I'll have to bring it further in. And to keep it at 44.8, I said, okay. Right. So, this time I have kept the knife edge not on the center of gravity of the meter ruler, 5 centimeter on the left side of it. Now, if I take momentum from this point, from this point in 5 centimeter, we have the weight of the meter ruler. Then 5 centimeter into capital Mg, capital MB, the mass of this meter ruler. Then this length, I can measure this length, this is at 49.8, this is at 66.5. So, that distance into M2 and the distance here into M1. So, M1 into L1 should be equal to M2 into L2 plus capital M into 5 centimeter. This capital M into 5 centimeter always the same because I am not changing the points. The center of gravity does not change, mass does not change. So, capital M into 5 is always going to be there, only thing L1 and L2 will change according to these two positions. So, this time when you keep it like this and if you draw the graph, you will get a straight line with an intercept. You will get a straight line with intercept. So, if you find the intercept, from the intercept we should be able to find the mass of meter ruler also. So, that is another extension of this same procedure where we do not keep the knife edge right at the center of gravity, we keep it a little bit displaced from the center of gravity and do this experiment, get another graph. From the graph, as usual, you can find, if you find the gradient, that has to be M1 over M2, you can find this M2, and additionally you can find the intercept. From the intercept you can find mass of the meter ruler also. So, that is another variation of this experiment. Plus another variation that we can add on this, we can keep this block or this stone into a container with liquid. The density of the liquid is unknown. If I am going to find the density of that liquid, I can submerge this stone into that liquid. What will happen when this stone is submerged? It will get an upthrust. It will get an upthrust. When the upthrust comes, the tension on this string reduces. So, the rightward momentum, the clockwise momentum reduces. To balance it again, I have to take it to different length. Like that, I can keep it, balance it at different lengths. I can change the length here and balance it at different lengths, having it submerged into the water or whatever that liquid. Then draw the graph. From the graph, if I have already found the mass of this, I can find the upthrust. From the upthrust, we will be able to find, if I can find the volume also, then we can find the density of that liquid. Right. So, the basic experiment I have done, I have taken the readings and I have shown you. There are two different extensions that can come on this, how to find the mass of the meter ruler or how to find the density of another liquid using this same setup. Right. So, be familiar with this. There are lots and lots of past paper questions on this same setup, same experiment. Try answering all those questions. You should be able to answer after going through these explanations. Right. So, that is all about this experiment. In the next experiment, we will see another concept in mechanics. All right, students, the readings we have got, I have put it in the table here. X and Y values we have. Let us draw the graph X versus Y. X in centimeter, Y is also in centimeter. Ten, 20, 25, 30, 35. 10, 10, 15, 20, so 5 should be here, 5, 0. 25, 30, 35, that is enough for us. And on the other side also you need up to 42.9. And we'll take 5, 10, 15, 20, 25, 30, 35, 40 can manage. 5, 10, 15, 20, 25, 30, 35, 40, 45. First one is 10 and 12.2. 10 and 12.2. 10, this is 12.5, a little below that. 12.2. 20, 24.4. 20, 24.4. 20, 24.4. Next one. 25, 30.8. 25, 30.8. 25, 30.8. Yes. 30, 36.9. Correct? Yes. 35, 42.9. 35, 42.9. 42.5 is here. 42.9. That's it. Let's draw the graph and see. It has to be a graph through origin, a straight line through origin. See whether we get that. Very nicely we get it. Almost all the points are on the graph. Almost all the points are on the graph. Very nicely we get it. All what we need is the gradient of this. Gradient. To find the gradient, let's take 2 points. This seems to be an ideal point. That's at 32.5 and 40. We'll take another point here. Maybe this point we can take. That's at 22.5 and 27.5. So gradient is going to be (40 minus 27.5 is 12.5, 32.5, 22.5, 10. Remember the graph, m naught g into x equals mg into y. That's what the graph is. So y equals m naught over m into x. M naught over m into x. Gradient has to be m naught over m. This is 1.25. So m has to be 1.25. No, m naught over 1.25. M naught is 50. How do you divide this? You multiply up and down by 8. The denominator will become 10. Then it's easy. It will become 400 over 10, 40. The known weight that we used was 50 gram and the unknown weight that we get is 40 grams. 40 grams. Clear? So that's a very simple experiment. Nicely you get the readings. I told you where and where the mistakes or errors can happen in the experiment. So by ensuring those errors do not happen, if you do the reading, if you do the experiment, get the readings, you will get a nice straight line graph through origin, get the gradient and you can find the unknown mass. Right? So that's all about it. Let's see how this has been tested in the past papers. Now let's see some past paper questions from this experiment. See, the first one I have taken, this is from 1999 paper. You are given the following to find the density of glass using the principle of moments by an experiment. A glass piece with irregular shape, mass m is approximately 50 grams. 4 weights of 0.4, 4, 40 and 400 grams. A meter ruler, a knife edge with fixed knife edge fixed on a stand, a beaker with water, a piece of string. Draw an experimental arrangement to find m by balancing the meter ruler in its center of gravity. Name the masses and their respective lengths L1 and L2 from the knife edge, which we know exactly the same thing that we did. Exactly the same thing that we did. See, this is the meter ruler. You are going to have the knife edge. And the knife edge is usually kept on a stand. Otherwise, you won't be able to hang the weights, the string, two strings. One is going to be the weight, the other one is going to be the irregular shaped glass piece, right? This is M glass, they mark it as capital M, isn't it? Capital M. They did not say which one has to be marked L1, which one has to be marked L2. We can take as we want. So, let me take this much to be L1 and this much to be L2. Right, that's all they asked. Draw an experimental arrangement to find M by balancing the meter ruler in its center of gravity. Let's mark center of gravity. We need to say G. This point is G. G, center of gravity of the meter ruler. What is the advantage of balancing the meter ruler in its center of gravity? What is the advantage of balancing it in the center of gravity? Then you don't have to consider the weight of mass. Why? We have already seen the normal reaction and mass of the meter ruler or the weight of the meter ruler will act at the same point. From that point only you are going to take the moment. So, there won't be a perpendicular distance for those two forces. So, primarily which one we are avoiding here? The weight of the meter ruler. So, the advantage is the weight of meter ruler, weight or mass, meter ruler need not be considered, need not be considered. Need not be considered. Which weight given in 2 above is suitable for this experiment? Give reason for your choice. Now see, we were given 0.4 gram, 4 gram, 40 gram and 400 gram. The mass of the glass piece is approximately 50 grams. 50 grams. You remember when we started discussing about this experiment, we said both weights must be comparable. They must be close to each other. The reason is, then only the lengths you measure on both sides, L1, L2 both will have a significant value like 40, if one is 40 centimeter, other one is also around 40 centimeter. If one is 45 centimeter, other one is also 45 centimeter. So, you can get larger values for L1 and L2 if these two are almost equal in size. Then what is the advantage? Fractional error can be minimized, because error in getting the length measurement, error divided by length that you measure is fractional measurement. So, if you take bigger length, larger length, then the fractional error is minimized. What will happen if you take 400 grams and 40 grams? When 40 gram is at 40 centimeter or 50 gram is at 40 centimeter, 400 gram will be at 5 centimeter. Understand? That's how the balance will come. When one is at 40 centimeter or 50 centimeter, other one is going to be around 5-6 centimeters. Right? So, then the fractional error in measuring 5 centimeter is going to be big. That's why we say both masses should be close to each other. So, which is suitable for us? Let's say 40 grams to get larger values for L1 and L2 and minimize the fractional error in measuring them. Fractional error in measuring them. Next, write down a formula for M in terms of M, L1, L2. Where did we mark M? Right, see, Simple M we have marked it as L1, capital M we have marked as L2. So, from G when you take moment, capital M into L2. Let's write it. From G you take moment capital M into L2, simple M into L1 will be 0. So, capital M will be equal to M L1 over L2, M L1 over L2. Without changing the position of the glass piece, what are the next experimental steps that you would follow to find the density of glass? To find the density of glass, now you have found the mass of it, right? From this method you have found the mass of it. Next, what you need? You need the volume of it. With this method itself, I explained it to you. How do we do it? See, this is how the meter ruler is. The knife edge is here. This is where the glass piece is. This is L2. And we had L1, the known mass was balanced. Now, what we do? We will take a beaker of water and immerse this glass piece fully into the water. When you immerse like this, what will happen? It will get an upthrust. It will get an upthrust. So, the tension here is going to be the weight minus upthrust. Agree? mg minus v rho wg. Now, again balance this and bring the known weight at a different distance. It won't be at L1 anymore. It's going to be L3, let's say. So, at L3, now if you take moment from this point, this is mg, simple mg into L3, capital Mg minus v rho wg into L2. From this formula, you already have found capital M. You know M, you know G, you know L3, you know capital M, you know G, you know rho W, you know G, you know L2. You know all the values other than volume V. So, substitute all the values, find volume here. Already you found the mass. From this formula, you are going to find volume. Mass divided by volume is going to be the density of glass. So, let us write the experimental procedures for this. What are we going to do first? Immerse the glass piece into a beaker with water. Let us say fully. Glass piece fully into a beaker with water. Change the distance of M from knife edge. Knife edge. Knife edge. And balance the meter ruler. That's all we have to do. That's all we have to do. That's what the experimental procedure is. Right? They ask, without changing the position of the glass piece, what are the next experimental steps that you would follow to find the density of glass? This is all. Then the calculation. What measurement would you take? Let it be L3. What measurement are we going to take? Distance to the mass M3, or distance to M from knife edge. Knife edge. Derive a formula for the density of glass rho in terms of density of water, rho W, L3 and L1. Let's see. Now we can write the formula. The one I already have written. This one. Mg into L3. Simple Mg into L3 will be equal to Mg minus V rho Wg into L2. L2 was not changed. You can cut the G everywhere. M L3 by L2 will be M minus V rho W. M minus V rho W. This M also I can substitute now. We can say V rho W comes to the other side, isn't it? So, let us rewrite it like this. V rho W equals M minus ML3 over L2. So, from this V can be written as M. Wait, M also we have already found it, isn't it? M we found it. Where was M? ML1 over L2. Let us substitute that here. M can be substituted with simple M L1 over L2. Correct? Right. So, you get V equals M over L2 can be taken common, L1 minus L3. This is the volume of it. So, density of glass rho has to be mass over volume. Mass is what you say M L1 over L2. Divide that by this M over L2. L1 minus L3. Correct? Where did rho W go? V rho W. We have to write rho W here. Let us keep it here for now. And then at this point, I will bring it down here, rho W. So, here rho W also. So, it is going to be M and L2 will be cancelled, rho W will go up, L1 rho W, L1 minus L3. This is what the density of glass piece according to what we have done. Now, look at the question again. They said give the answer in rho W, L3 and L1 or L2. Why did they say O L2 here? Imagine in the initial diagram, he did not say which side has to be L1, which side has to be L2. I marked L1 here. Suppose if another student has marked L1 on that side, L2 on this side, now instead of L1 in the answer, he would have got L2. Understand? Because of that only he has mentioned, the examiner has mentioned here, you can give it in rho W, definitely it's there, L3 it's definitely there, L1 or L2, L1 or L2 can come. Right. Next. Another piece of glass made out of the same material but having an air bubble in it has a mass of 100 gram. The density calculated using the above method was 2 into 10 to the power 3. Now this is going to be an issue. Why? This is a glass piece and it has an air bubble in it. But this method, when you measure the volume, you are going to take the entire volume. You are going to take the entire volume. Whereas there is a glass bubble, air bubble, right, let me say VA. So, actually V minus VA should be the volume of glass. But when you immerse it in water, the entire glass is going to be immersed in water, right, including the air bubble. So, the displaced water will be equal to, the volume of displaced water will be equal to the volume of the entire thing, including air bubble, because air bubble is in the middle of the glass piece. So, now look at this, the density they have calculated is this. So, let me say rho equals M over V. So, the density they have got is 2 into 10 to the power 3 equals 100 grams, 10 to the power minus 3 over V. Here the V is the total volume, You solve this, V is going to be 50 into 10 to the power minus 6 meter cube. They are asking you to find the volume of air bubble, but they said the actual density is 2.5. When you say the correct density, We have to take the volume excluding the glass air bubble, excluding the air bubble. So now I will rewrite the formula. 2.5 into 10 to the power 3 has to be 100 grams of over V minus V naught. So V minus V naught, if you divide it, you will get 2.5, 40 into 10 to the power minus 6 meter cube. So you subtract, you get V naught 1, 2, 1 minus 2, V naught is 10 into 10 to the power 6 minus 6 meter cube. Why I wanted to keep 10 to the power minus 6 is, if you want to convert this to centimeter cube, 1 meter is 100 centimeter, 10 squared centimeter. Cube means thrice of it, 10 squared, 10 squared, 10 squared, it will become 10 to the power 6. So this 10 to the power 6 will be cancelled. We can say 10 centimeter cube is the volume of air bubble within it. Clear? That's a very nice question, simple question that has come in 1999, testing the basics, basic knowledges on the experiment. Now let's see another experiment, another one on the same, another question on the same experiment. This is from 2017 paper. You are asked to find the mass m of a piece of rock of irregular shape having a mass of T, having a mass of the order of 60 grams by performing the experiment, which uses the principle of moments. You are provided with only the following items to carry out the experiment. A similar thing again, let's see. A weight of mass 50 gram, meter ruler, knife edge and a suitable wooden block, pieces of thread. As the first step of this experiment, you are asked to balance a meter ruler on the knife edge. What is the purpose of this step? To find the center of gravity of meter ruler. To find the center of gravity. To find the center of gravity of meter ruler. Center of gravity of meter ruler. Draw a diagram of the arranged experimental setup on the table shown below for the balanced situation just before you take a reading. Mark the balanced length L1 and L2 correctly. Take the larger balanced length as L1, larger length as L1. Measures from the balanced point in the diagram. Label the items. Right. So we will draw the wooden block. On the wooden block, we will draw a knife edge. Keep it properly. Then the meter ruler. Right. You're going to have two weights. Look at this. One, I draw it a little closer. One, I draw it a little longer because one is 50 gram, one is 60 gram. So 60 gram will be closer to the knife edge compared to 50 gram. Right? 60 gram. What is 60 gram? The glass piece, is it? It's a glass piece, or what was it? Mass m of a piece of rock. Okay, piece of rock. Piece of rock. Right? And here you have a weight. How have they given the shape of the weight? Like this. Okay. The weight. The distances L1 and L2, they say larger one has to be L1. So this is L1. This is L1. And this is L2. L2. Write down an expression for L2 in terms of M, L1 and when system is balanced. When the system is balanced. Simple. Let's mark G there. G. From G, when you take moment, right, this is what they mark as, which one is M? 50 gram is M, other one is capital M. So this is capital M, this is simple. 'M'. simple M L1 minus capital M L2 is 0. Or we will put G as well, then we can cancel it. Mg L1 capital Mg L2 is 0. So, capital M, now they are asking you to make L2 the subject of it. L2 will be M L1 over capital M. M L1 over capital M. Simple. You are supposed to draw a graph in this experiment. What position of the meter ruler would you place on the knife edge every time when you take a different set of readings for L1 and L2? You have to ensure every time the meter ruler has to be balanced on its center of gravity. So, we need to find, like initially when we balance it, we would have found where the center of gravity is. Every time before you take the reading, you have to ensure knife edge is at that same point, right? So, what position of the meter ruler would you place on the knife edge every time when you take a different readings for L1 and L2? The center of gravity which was identified initially. That's for the initial step of it. Initially. Suppose you have plotted a graph as shown in figure 1 to find the mass M. Alright, you can see the graph L2 and L1. What was the equation we had? We had L2 equals M L1 over capital M. Okay. So, L2 and L1, then the gradient will give you simple M over capital M. Gradient will give you simple M over capital M. In this experiment, you have been asked not to take readings for small values of L1 and L2. What is the reason for this? To minimize the fractional error, because if you take L1 and L2 large, then the fractional error can be minimized. So, let us say to minimize or to minimize the fractional error in reading L1 and L2. In reading L1 and L2. By selecting the two most suitable points on the graph, calculate the gradient of the graph given in figure 1. The 2 points selected should be clearly marked on the graph using arrows. Let's take 2 points. Let's take 2 points. I think this is a good point. Like when they say suitable points, the point we take on the graph should be on a vertical line and on a horizontal line. Then you can get the readings precisely. So, I think here we have a point here. This is 10, 11, 12, 13, 14, 15, 16 and here 13. Similarly, do we have another point anywhere else? Let us see here. That is 39 and 31, 31, 39. So, 31 minus 13 31 minus 13 over 39 minus 16. So, this is 18 by 3, 2, 23. Am I right? 9, 6, 3, 3, 1. 18 by 23 is the gradient we are getting. Right? We can keep it in fraction itself, because next time we will have to equate this to M over M. Yeah. Calculate the mass. So, gradient is M over capital M. That is what you have got it as 18 by 23. 18 by 23. So, capital M is going to be M into 23 over 18. M was given to be 50 grams. Right. So, this is going to be 9, 25. So, 25 into 23, 75, 50, 575. that 575 divided by 9, 6, 54, 35, 3.89. 63.89 grams we are getting. 63.89 grams. 63.89 grams to the closest 2 decimal points. You are also asked to find the mass m naught of the meter ruler using only the other items provided above except the piece of rock. Draw a suitable diagram of an experimental setup that could be used for this situation in the space given below. The center of gravity of the meter ruler should be clearly labeled as G. You can't use the rock this time. So, you have the meter ruler and the known weight of 50 gram only. What shall we do? What shall we do? Right, look at this. This is your meter ruler. Let's say this is where your G is, center of gravity is. Now, what you do? All this time we were balancing the meter ruler on the G itself, right? Now, if you want to find the mass of meter ruler, then we should not balance it at G, because when you take moment from the point where it's balanced, mass also goes through that, weight also goes through that, it doesn't come. So, what we will do? We will shift it a little bit, right. Now, what will happen? The meter ruler will try to fall. It will rotate clockwise because the mass is going to be here. If I mark that, the weight is going to be, the m naught G will act at this point, m naught G. So, from this point where you have kept this balance, kept this knife edge, it is going to rotate. How do we prevent it? That is why we have a weight. We have a weight. Fix that weight on this side. Fix that weight on this side, right? And adjust it such that the system balances. Adjust it such that system balances. Now, you can say this is x. M naught G into x will be the mg into L. This L you can measure, mg do you know. So, mg into L you know, m naught G into x, x you can measure, only m naught is unknown. They didn't ask you to explain everything, they asked you to draw the diagram only. This is enough. Mark G clearly. Meter ruler using the other items provided above except the piece of rock. Draw a suitable diagram of an experimental setup that could be used for this situation in the space given below. That's it. That's it. And they ask you to mark G clearly. Done. See, so these basic experiments like what you get from mechanics, what you get from waves and oscillations are pretty straightforward questions. Right, there is, if you know the basics, problem is basics. If you know the basics, if you have understood the basics, then answering these questions will not be a challenge at all. Practice all these couple of times. Let's meet up in the next session with another experiment.